our previous experience with a Slurm and MPICH based malleability prototype. Hopefully, we don't spend too much time per slide because, in my experience, this presentation has, in the past, but also recently, had a trial run, and it always triggers a lot of conversation. At the same time, just go ahead and interrupt me if you have anything that you want to say in the middle of the presentation. So let's go to the next slide. So what is then the motivation behind malleability? So as you may have experienced, some algorithms have scalability ceilings that change during execution. So the application may be holding resources that are being underutilized or just not used at all during lapses of time. But as well, it could happen that during execution, the application increases its scalability potential. It could be using more resources. So an example of that is an adaptive mesh refinement algorithm where it does a lot of refinement, but it could also happen during the execution that it can do coarsening, so not only refinement. And so this basically changes the size of your domain and therefore the potential number of resources that you can use efficiently. Also this is from the side of the application, but also from the side of the resource manager. Every time, well, basically all these supercomputing resource managers today, they do this FIFO scheduling with backfilling and usually with priority support. But basically the allocations come fixed. So something you can do is to make them moldable. That means that you can start them at different allocation sizes. But then if you also do malleability, then you can change this allocation size during execution. And so the advantage of having this flexibility is that now you can, if you have nodes available, you can fill them. And also, if you have a high priority job, you can also make space to start as such a high priority job without preemption. You can push forward the start time of a job if you have the flexibility of shrinking the allocations of others. And so this allows you to minimize the idle node count, which is a usual efficiency metric for these schedulers. Let's go to the next slide. So something that we did that is not relevant to PMIx was to come up with an experimental API and for MPICH, and this is not part of the standard, so I should have written here MPIx, not MPI, because if you come from the MPI community, you will know that if it's not standard, we are supposed to put an X here. Sorry for that here. But basically what we did was to have a new way of initializing the library and then have an operation that probes for changes and then a transaction API. In this case, we are missing the abort operation. So we only implemented the begin and commit operations. And so this allows you to repartition the domain of the application and then continue execution. The init adapt operation will tell the processes whether they are new processes that are just started execution. So that means that they are the first set of processes that are computing in the simulation, for example. And then there's a second case where the flag will tell you that you are actually a process that is supposed to join a pre-existing group of processes. So this is why we needed to make a new initialization procedure so that we can pass in this additional flag to process to make this extension. The second operation is meant to be used by pre-existing processes. So they basically probe the system to check whether there is an allocation update. And the allocation update could be both a shrink operation or an expansion operation, or potentially even a migration. But with this operation, you only get the flag of if there's anything to be done. The actual detail of the operation is given to the application when they call the MPI adapt begin operation. So how this looks like more or less in the code structure, then is as shown in the code structure block here on the right. So you're expected to call init as a normal MPI application and then enter some kind of computational loop that is usually in simulation is a time loop. And then from time to time, you're supposed to check if there's any changes to your allocation. And then if there are any, then you're supposed to open up this transaction with the begin and commit operations and adjust your partition and everything else necessary, any kind of metadata updates that you may need in your application, so that you can continue executing correctly after you have repartitioned your domain and so on. So let's go to the next slide. So in the next slides, I will describe how we implemented it. So what you have is the typical Slurm design, where you have the controller daemon that loads the scheduler, among other things. And then you have, in an allocation, you have the leader nodes, which is the node with relative index 0 in an allocation. This is a special node in Slurm because this is where the batch script is forked. So it's only forked in the leader node. And then in there, as you are launching applications, then an SRun instance will be created. And so SRun is actually attached to the node of index 0 of your allocation in the Slurm design. And what will happen is that then SRun communicates with the Slurm daemons to fork necessary Slurm step daemons on each node. And then these Slurm step daemons are the ones that fork the actual MPI processes. And so in this example, we're illustrating here 4 MPI processes per node. So when there is, in our design, the malleability decisions were triggered by the scheduler itself. So it's the Slurm controller daemon messages the application via the SRun instance that it belongs to. So this is the first step. Let's continue to the next slide. The second step is difference between an expansion of an allocation or a shrinker of an allocation. In this case, we're illustrating what happens in an expansion of an allocation. So the first step is to notify the Slurm daemons that are monitoring the node of the expansion allocation. Let's go to the next slide. So the reason we do that is because we want to pre-fork MPI processes before interrupting processes that are doing progress. So the pre-existing processes are the ones that are doing useful things. So we want to allow them to continue. So what we do is, when we are going to give more resources to the application, we want to pre-fork these processes. So then they get forked from their Slurm step demos, as I described before, and then they call the MPI needs adapt API, and they get a flag saying that there are processes that are supposed to join pre-existing processes that are already executing. So therefore, they don't go through the normal initialization of the application. Instead, they go ahead and call MPI the begin operation, begin operation of our API that we described before. And what happens is that they block in there. And an event is then generated for SRun. This is what you see here in number 3. SRun gets notified when these processes are ready. So let's go to the next slide. So once this happens, then we send a notification to all the pre-existing processes via their daemons. So SRun itself sends this message over the overlay tree network, and this reaches all of the daemons that are participating, and therefore they notify the local processes. The local processes check for this with a probe operation, and then when they see that it is true, that there is a change in the allocation, they also call the MPI com begin. And so then at that point, then the 2 process groups have an intercommunicator available where they can exchange metadata, including new slices of their domain. In this case, it will be relatively easy repartitioning, because you will basically be giving half the domain to the new joining processes. So each process will basically give away 1/2 of their domain to a new process, for example. So let's continue with the next operation. When this, yes, with the next slide. So when this happens, when the repartitioning happens and the application has determined that the domain is now consistent and they can continue execution, they collectively call this commit operation, and this then notifies SRun, and SRun finally notifies the scheduler program. Let's go to the next slide. So the end of the malleability operation in this case is completed, and then the scheduler gets notified. So it is important to have this notification, because we don't want the scheduler, we don't want to allow nested malleability operations. So we want only one malleability operation to take place at a time. And therefore, the scheduler will not send instructions on multiple operations until it gets the confirmation from the previous one. So that's a limitation that we introduced. So let's go to the next slide. So something that happens with all these malleability experiments is that the system becomes really dynamic, and it's very difficult to understand it. So something we did was that we linked the OTF2 library, as some of you may be familiar with. This is what is used with Vampire and Scorpion and so on. So we basically linked this into the scheduler, and we started generating traces of the jobs themselves. So as you may imagine, this is very different than MPI communication. So the traces are actually quite small, which is good. And then with these traces, what we can observe is with the already existing visualization tools that we have for OTF2, is that we can see what actually happened in the system. So in here, we have two examples. The one on the top is a situation where you have two jobs, job 78 and job 79. And then what happens is that job 78 gets one node that is then exchanged with job 79. So basically, job 79 goes from 2 nodes to 1 node, while job 78 goes from 2 nodes to 3 nodes. So what you may observe here is that we do the shrink operations first, so that the node becomes available, and then we pass it to an application that may have an expansion of the allocation. So this is what you're seeing here. Below, we are seeing a system that where an application was started with a single node, and because the nodes were available, so they were idle, and the scheduler basically triggers an expansion of its allocation to the full set of 4 nodes. So in that case, what you can observe in the kind of light green or yellow color below is the behavior where we pre-fork the processes. So you can see that the processes of the 3 nodes are on expansion. They have been forked before the processes on the top were notified. So this is what you can see by the yellow, greenish, light yellow area on the top on the first node, is that the actual interruption to the execution happens a little bit afterwards. So the pre-fork definitely takes place before the existing processes are notified. Let's go to the next slide. So why is PMIx important in malleability? So what happens in a typical MPI, at least with MPI, typical situation is that the interaction via PMIx with the system happens at the beginning when you are creating and bootstrapping the processes. So in malleability use cases, this will be more periodic, maybe not periodic, but it could happen at any time in execution. So these overheads related to PMI, so this interaction between the resource manager and the runtime system, it's not only one time, it's multiple times during the execution of the application. So the efficiencies here become more important because they are higher impact now. Whereas in the usual case, it only happens once. So you just start the application and you start monitoring that the processes don't crash. But other than that, you just let it run to completion. So in the malleability case, we also see the need for more feedback and control mechanisms. So as I said, in the static case, the application starts running and we just pay attention until it completes, so that no processes crash, for example, and stuff like that, but not really active interaction. Whereas in the malleable case, we will be interested in getting some performance feedback, for example, to get a rough idea of how efficiently the application is using the resources. When later on we may actually take resources, or we may observe that the application is actually has some potential for scaling out, and therefore we could also give some resources to it. What can also happen is that the application can be requesting resources dynamically. So the application itself will be interacting with the resource manager frequently based on what it's seeing in its own execution. For example, if you're doing adaptive merge refinement, it could be that the application has observed that there has been a significant amount of refinement in the domain, and therefore it could use more resources efficiently, so it could actually trigger this negotiation with the resource manager as it's executed. So there's much more interaction between resource managers and applications in the malleability use cases. Something else that is very important with PMIx is that we, as you know, MPI is relatively static. So we don't want the solutions to be like in this example where it's a really an MPI-centric solution. We want to decouple the malleability support from the MPI model itself. Although there are discussions to make MPI support malleability, this is ongoing now in the sessions work group. But we want to basically be agnostic here. We want to support any kind of emerging programming model. And there are some programming models that have been static because they actually link MPI in them. So if we actually remove MPI, they could actually become malleable themselves. So let's go to the next slide. So this malleability within PMI. So far, we are really early in the conversations in the tools work group. So this is something that we are working on in the DeepSea project. And what is surprising to me is that most people agree that we need something like a transaction API, similar to what we designed here in this prototype with this so-called begin and commit operations, but also with the addition of an abort operation. And the motivation behind a transaction like API is that the change of your domain to a new set of resources can be a potentially dangerous operation. So we want the applications to have an opportunity to give up. So, and do some testing before the application commits to a new set of resources. So imagine you have a simulation that is running already for several hours, maybe even more than 10 hours or even days in some cases. And then of course, you want to be able to use more resources if you can, but you wouldn't want to risk failing and then losing all that progress. So of course, you can also make a checkpoint before you do the malleability operation, but in case that you want to do it a little bit quicker without, or maybe you don't want to be blocking on the file system, maybe you can do the checkpointing asynchronously. You can also then, let's say, have the flexibility or that is given with malleability, but at the same time having the safety, the other safety of doing it in a transaction API that you can always just give up and continue your progress with the existing resources that you have. So it seems, I was actually surprised that at least in our tools work group and the communities in the European project, it looks like people are in agreement. This is something that was not expected from my side. The other point that we have also agreed with is we have consensus is that we want to support both the malleability operations from the negotiation point of view to be driven from the resource manager and also to be driven from the application. So we don't want to commit to only the resource manager doing it or only the application doing it. So we want to allow both. And the motivation behind that is that from the resource manager view, you have the system view, while the application has additional information from itself that the resource manager doesn't have. So it could be that in some cases, the resource manager is the one that has the relevant information, whereas in other cases, the application is actually the one that may have any kind of information about how many resources it could use efficiently and so on. So there's this separation between what's actually the negotiation side of things, where it can be started from the resource manager or started from the application, and the actual operation that results in a remapping of the resources of an application. There's a separation there, and I think so far we are in agreement on this. The last point I have here is that we will be making a prototype within this European project. Something that is also interesting is that it's not only one European project that is looking at malleability. it is a deep sea project, but there are at least 2 more European projects that are looking at this. And so it looks like we will have enough people to make a quality prototype, because there's, as you may imagine, many things need to be updated for malleability to work. So you need to change the resource manager, the scheduler, but also runtime libraries and applications, and also tools. So if you want to have any chance of getting this, developing an application that is malleable, then you need parallel debugger support and so on. Let's go to the next slide. So just to summarize, in the past, we did this alternative to MPI dynamic processes. This is what I described with the initialization API, the probing API, and also such a transaction for the actual change of resources within the application. And as you have seen from the node traces, we did achieve this latency hiding this time from the view of pre-existing processes that are doing progress. The latency of the creation of new processes, getting the allocation, all the scheduling overhead and so on, all of this is hidden from the application. So then the actual, from the view of pre-existing processes, the actual dominant overhead became the repartition of the domain, which is what we were looking for. So we were successful on that. And the next point is that we are going to be driving the prototype work within the Deep Sea European project. So what we did before was based on MPICH, a really old release several years ago, something like 4 years ago. So this time it's going to be on a recent release of Slurm Open PMIx instead of PMI2 that we used before, and also Open MPI and MPICH. Both of them we're going to make prototypes to make sure that this approach works in both implementations. And something else to measure, I know some of you participate on the MPI sessions working group. So we're actually active there. The situation there is, I think it will take a long time to get an MPI proposal. So it looks like, given our schedule, we're going to be working on non-standard MPIs, at least at the beginning. And if you are interested, I included here the 2 main publications of this research. And that's it from me. I'm open to questions.